Nearly half of California's landmass is covered by harsh, arid desert. Yet, out of that dry terrain, the state produces more than 70 million tons of agricultural products every year, dominating a food supply chain that feeds over 340 million Americans. To make that output possible, the state forced nature to serve the land. Over the last century, massive engineering networks like the historic LA Aqueduct and the 700-mile California Aqueduct were built to pull melting mountain snow and distant rivers directly into dry valleys. The Imperial and Central Valleys now produce nearly all of America's winter leafy greens and 40% of its fruits and nuts. That entire volume of food is packed into a region that accounts for just about 1% of the total U.S. farmland. But alongside those fields live 39 million residents in a state where water resources are continuously pushed into a state of red alert. California successfully engineered an agricultural miracle. But it relies entirely on drawing from a finite, shrinking water supply to keep the dirt green. Cultivating high-value exports requires an enormous baseline of resources. A single avocado, for instance, consumes roughly 320 liters of water before it reaches commercial maturity. Other crops demand immense logistical force. California produces billions of pounds of almonds annually. To sustain that yield, over 2 million honeybee hives must be trucked in from across the United States every spring just to pollinate the orchards. This chart compares the water demands of seasonal vegetables against perennial crops. With an annual crop like lettuce, farmers can choose to leave a field unplanted during a dry year, but an almond orchard takes 3 to 5 years to reach yield. Once planted, farmers are trapped, forced to irrigate year after year. Zooming out to the state's total water budget, agriculture now consumes 80% of the water used by humans in California. The immense profitability of these crops locked in the region's choices. To keep those orchards alive, the agricultural sector is forced to spend natural water reserves it can barely afford to lose. To justify these massive input costs, traditional farming evolved into a hyper-efficient, high-volume industrial machine. Manual picking has largely been replaced by speed and raw power. Giant mechanical tree shakers clamp tightly onto trunks, bringing down an entire canopy's worth of almonds or plums in a matter of seconds. For high-volume processing crops, giant self-propelled harvesters drive straight through the fields. In a single pass, they continuously cut, separate, and load millions of tons of tomatoes and green sugarcane directly onto moving trucks. Other methods use water physics. During a cranberry harvest, farmers flood the bogs to detach the berries. Tiny air pockets inside the fruit cause them to rise, creating a dense floating carpet that can be rapidly swept up by rotating conveyors. These machines represent the pinnacle of mechanical output. It is a highly tuned logistical system built to process crops at high speed and extract maximum economic value from the soil. But machinery only solves the extraction. Fragile produce like strawberries and zucchini begin losing water content and crispness the exact moment they are severed from the root. The harvest is an immediate, brutal race to get the produce sorted, packed, and loaded into refrigerated cooling facilities before decay sets in. By utilizing different climate zones that overlap as seasons change, this logistics machine runs continuously, dominating the national supply of fresh greens and berries nearly year-round. Yet this entire optimized supply chain remains completely exposed to a variable it cannot control: increasingly erratic global weather patterns. Over the past decade, the frequency of extreme rainfall during harvest periods has increased by more than 40%. Just one unpredictable storm can trap heavy harvesting equipment in the mud and leave millions of tons of crops to rot directly in the floodwaters. When the climate actively turns against the fields, high-speed machines and perfectly timed logistics are no longer enough to save the harvest. We cannot manufacture more fresh water, nor can we generate new arable land. To maintain the food supply, the exact variables of how food is grown have to change. This diagram illustrates the efficiency of vertical hydroponic systems like hydrogreen, which grow crops in nutrient-rich water without soil. Just 12 advanced vertical units can achieve up to 95% water savings, while matching the daily output volume of 400 conventional acres. Other concepts remove the land entirely. Experimental models like Nemo's Garden use submerged, dome-shaped greenhouses below the sea surface. They utilize natural underwater pressure and temperature to create stable, pest-free environments for dozens of plant species. These systems demonstrate that consistent, high-quality agricultural yields are possible while accumulating only a fraction of the historical resource debt. To secure the global food supply, these controlled environments are now being scaled up into massive industrial infrastructure, starting with protein. Off the coast of Norway, engineers have deployed a next-generation offshore salmon farm. Built to withstand 33-foot waves and stretching taller than the Eiffel Tower, the facility holds over 22 million pounds of fish in independent tanks. Back on land, indoor vertical farms are combining artificial intelligence with robotics. Systems powered by networks like PlentyOS use special foam pads, smart sensors, and automated robotic arms to push leafy green yields up to 350 times higher than traditional dirt farming. Traditional fields and mechanical harvesters will remain essential tools, but the systems required to feed a growing population without draining the planet's remaining water are no longer expanding into the desert. They are being built inside automated warehouses and anchored in the open ocean.